I was at the first one of these meetings in Paris in 2019, and I spoke, and I was a fresh-faced postdoc, to paraphrase Arjun, and I thought to myself, I'm completely outclassed in this speaker list, and now I'm a decidedly less fresh-faced associate professor, but I still feel completely outclassed. So thank you very much for this opportunity, and the Simons Foundation has changed my academic life with this project, so thank you very much for that as well. I'm going to be talking about the Robin green functions and the lung, and this is a project which is new for me because it started extremely sort of applied and concrete, but then it immediately became sort of the abstract mathematics that I love, so I'm very happy about it. And of course, it would have been impossible without the help of the Simons Foundation. So let me first start with something very concrete, which is the graphs that Svetlana alluded to yesterday. So if this is sort of total absorption of oxygen, and this is maybe the, I don't know, local absorption of the lung, right? So how much of the lung is working or not working in any sort of given moment. And actually, I want it to sort of be working 100% here and 0% here, which I know is a little bit of a silly way to draw the picture. Then both sort of observationally, when we look at patients who have lung problems, but also verified numerically by work of Marcel in the 2000s, this curve sort of looks almost constant for a very long time, and then at some point drops off very sharply, okay? So you can really have a serious amount of lung damage. You can be a 5 packs a day smoker, but you don't really notice it when you're just sitting around until you're in real trouble. Of course, if you're a professional cyclist, maybe you notice it a little bit earlier, but that's not what we're talking about today. So this is real fact. I know that we don't like that word, number one. And real fact number two is that for mammals, the lungs are fractals. Fractals is a dangerous word because it means a lot of things to a lot of people. So maybe let me tell you what it means to me. If you look at the surface of a lung, which I'll sort of draw in this spiky way, and you look at a ball centered at a point on the surface, and then if you look at the surface area of this ball of radius r, it will sort of grow like r to the alpha, where alpha is bigger than 2. And in fact, the alpha that you get is different for different mammals, but for humans, the alpha is around 3. And this has also been sort of, you can see lungs, you can open them up. And yeah, so this is also another real fact. Of course, this isn't true for every R, because at some point R gets smaller than the length scale, right, the cellular scale, and then alpha becomes 2 at that small scale. So maybe I want to say something like R bigger than cell scale, and the surface area of a ball is roughly R squared when R less than or equal. Cell scale. Okay? This is what I mean by a fractal. Okay, so these things have been observed in real life, and they've been worked out numerically and sort of understood physically by work of Marcel and his collaborators in the 2000s, but we wanted to understand mathematically why are these two things true. And so that's sort of the purpose of today's talk. Okay? Great. Fantastic. So I should say that all of this is joint work with Guy David, Stefano Decio, who's a postdoc, who's in the audience, I guess myself, Svetlana, and Marco Michetti, who's also a postdoc in Rome. And then I also want to single out Marcel, who I sort of thought of as our spiritual guide throughout this entire thing, it turns out it's a lot easier to prove theorems when someone tells you what theorems are true at the very beginning. So physicists really have a great role in mathematics. They tell us what's correct, and then we sort of figure out why for the rest of it. So yeah, I would love to have Marcel on retainer for the rest of my career if I could. Great. So let me write down a mathematical model. We have some sort of source of oxygen, which we normalize to be 1. This you should think of as the windpipe, if you'd like. And then there's some fractal surface around on the outside, right? This fractal surface satisfies these two properties. We can do more general things as well, but who cares for the purpose of this talk? In the middle, we have diffusion. So, I should say UA is something like the local density of O2, or something like this. And then on the boundary, we have some sort of partially absorbing condition, right? Because sometimes the oxygen hits the boundary of your lungs and gets absorbed into your bloodstream. Sometimes it gets bounced back. It gets bounced back more often if your lungs are doing worse. So we represent this by Robin boundary conditions. And what do we want to understand? The total absorption, right? So we want something like, if I call the outside of this partial omega, we want the integral over partial omega of d nu UA. Call this Fy. Okay, the physicists are probably mad because I probably haven't normalized things correctly and all the units have gone away. We can pretend that I'm like Arjun and I understand the units, but I'm simplifying things for the mathematicians, but actually, despite Marcel's best efforts, I have no idea what any of the units are. Okay, fantastic. Let me do a little bit of fine print. If you don't care about the technical details, you can tune out like you usually do with fine print. But I think some of these technical details are mathematically interesting. So a little bit of fine print. All of our theorems will work for divergence form operators. Sometimes A will have to be, well, it's always going to have to be elliptic. Sometimes symmetric, but it never has to be smooth, which is a mathematically very interesting aspect of our talk, but maybe is not so physically interesting. I'm not so sure. And another piece of fine print is that we need some topological assumptions on our domain omega, right, which is the sort of tubes that carry air into your lungs. Basically that it's quantitatively connected and no cusps. It's a one-sided NTA domain in the sense of Jerison and Koenig. Yes, please. I love that question. So the question, just to repeat it, is does it have to be flat space or can it be a metric which is curved? You can consider it sort of locally flat and then incorporate the influence of the metric inside of this variable coefficient, if you'd like. And you pretty much get everything that you want in that situation, right? So if you're sort of a smooth manifold, then this is the Laplace-Beltrami operator on that smooth manifold, which you can always write in coordinates in this way. If you're asking if there's any influence of like global topology, things like genus or stuff like that, no, we didn't think about that. Yeah. Other questions? Oh, sorry. Ah, great. That's not quite true. Sorry, to repeat the question, the question was if you have a source in enclosed space, everything should be absorbed. So why is there anything to compute? The answer should just be constant. But the air can go back out through your windpipe. And so that's sort of what you're trying to figure out, is how much goes back out. Yeah. Great. Fantastic. Maybe I should say, in your direction, it would be extremely interesting to understand the time-dependent version of this problem, where you understand like how long it takes things to leave the boundary. But we're just starting here. We'd love to do that in the future. But I don't have anything to say about time today.
Quick question. So it reminds me very much of this harmonic measure in 2D.
Yes.
But there are fine structures of harmonic measure, and then some robust things like support measure. So what things are you interested in? What's important?
I'm going to talk about that in 35 seconds. So, so actually, so our first try to explain this was to consider what we call Robin harmonic measure. So again, I have my domain omega. I pick some point, which I'll call the origin, in the middle. And then I define omega 0 r of E as the probability that a Brownian motion first exits omega in E, but this is partially reflecting. So your Brownian motion moves around, and then it hits the boundary, and with probability p, it gets absorbed, and with probability 1 minus p, it gets reflected back into the boundary, right? So maybe it gets absorbed here, but maybe it goes back and then continues on, and so on and so forth, right? And the relationship should be that A is equal to P over 1 minus P, where this is the probability of absorption. Great. And so work of Marcel in the 2000s suggested that there should be some phase transition, that if you look at what parts of the boundary are seen by the Robin harmonic measure, this should change as A goes from 0 to infinity, right? Which is sort of exactly what you were talking about. So to explain that a little bit to people who haven't thought about harmonic measure so much, let me give you a primer on Dirichlet harmonic measure, which is what happens when you're always absorbed, right, with probability 1. So this, on a personal note, is why I like this project very much, because I wrote my thesis on Dirichlet harmonic measure, thought it had nothing to do with anything, and then it turned out it had everything to do with lungs. So it was great. Yes? This graph.
So the point would be to show that on this graph, f of a is a function of p.
Yes, exactly. Yeah. Great. Can I erase it? Yeah. This is great. Okay, so Dirichlet harmonic measure is exactly this same thing, the probability that Brownian motion first exits your domain, but you always get absorbed as soon as you touch the boundary. So omega 0 d of E is the case, what, P equals 1, A equals infinity. This is an extremely well-studied object. It has connections to sort of conformal geometry when you're thinking about domains in the plane. But even in domains in R3 or Rn, it's interesting because it tells you things about the well-posedness of the corresponding boundary value problem. right? So if you want to understand the solution to something like this, it turns out that you really want to understand the behavior of the Dirichlet harmonic measure. But I don't want to get too much into this because it's going to get me too far afield. What I do want to talk about is a phenomenon known as dimension drop, which is exactly sort of what was being alluded to before. And the idea is that these Brownian travelers don't see the entire boundary if the boundary is too thick, right? So what do I mean by this? I mean, so here's a sort of preliminary or a sort of classic result in that direction by Jones and Wolff. And every time I mess up this reference, so I finally wrote it down, in 88, which said that if you have a domain omega in the plane, and you look at the dimension of the, or maybe I should say, there exists a subset of the boundary such that the harmonic measure of the boundary minus the subset is 0, and the dimension of E is less than or equal to 1. So the boundary itself could have this, oh, I erased it, but could have this fractal dimension bigger than 1, right? It could be like a Cox snowflake or something like this. But the Brownian travelers don't care. They only see a portion of the boundary, right?
Sorry, so you mean literally 0 for like the harmonic measure?
Yes, literally 0. So there's, I mean, it doesn't mean it doesn't happen, right? But it happens with probability 0 that the Brownian traveler would exit the, yeah.
The measure depends on the, unrelated question, depends on the release point. Right?
Yes.
Saying it's the origin of the whole.
The measure depends on the release point, but if the domain is connected, having measure 0 is independent of the release point by the Harnack inequality, if that's a word that people like. Basically by the fact that harmonic functions with non-negative boundary values don't vanish in the domain. Great, yeah. Fantastic. And then in fact, this phenomena of dimension drop was sort of well studied in the plane, especially by a number of different people. I sort of don't want to list the whole list of names because I feel like I'm going to miss some. But the story was more complicated when n is greater than or equal to 3, and omega is a subset of Rn. There's a result of Bourgain, 87, I believe, which says that there exists some number which depends on the dimension, such that for all omega in Rn, there exists an E subset of the boundary, such that the harmonic measure is concentrated on E, and the dimension of E is less than n minus epsilon n. So if you'd like, Jones and Wolff is telling you that epsilon 2 is 1. Okay? But this is, I mean, this is much less effective, right? We have no idea what epsilon 3 is. This is a major open problem in the field. But there is a counterexample of Wolff, which says there exists an omega in R3, and such that if E is a subset of the boundary and the dimension of E is less than or equal to 2, then the harmonic measure of the boundary without E is positive. So Wolff tells you that epsilon 3 is not equal to 1. It has to be smaller than 1. So this question of dimension of harmonic measure is extremely interesting. Let me just sort of point out that the expectation is that if sigma of balls acts like r to the alpha, and alpha is not an integer, then we should expect there to exist a subset of the boundary where dimension of E is less than or strictly less than alpha, and the harmonic measure of the domain is concentrated on E. So somehow the phenomenon is that if you look like a fractal, you should miss some portion of the boundary. This has been proven in some instances. There's a very nice paper by Jonas Azam. And if you will permit me a little bit of promotion, it was actually disproven in some other interesting cases by recent work of Guy David, my PhD student, joint with Svetlana Koljesnak and Antoine Julia. Gave a counterexample to this expectation. But somehow this counterexample is quite special. The idea is that sort of in general, especially if alpha is bigger than n-1, you expect dimension drop to occur. Okay. So if we go back to, maybe I should leave this here, right? That's good. You can ask the question, does Robin harmonic measure exhibit dimension drop? Right? Maybe this is what's going on with the curve that I erased before and the fact that we have fractal lungs. That sort of, for some values of A, you see the whole boundary, and then for other values of A, you don't. No. So here's a theorem, which is due to this whole crew, which was put out last year. There exists a constant C. C depends on A and maybe the geometry of omega, such that the Robin harmonic measure of any set E is bigger than C inverse times the surface measure of that set E and smaller than C times sigma of E. So in fact, we showed that almost the opposite phenomenon of dimension drop occurs, that Robin harmonic measure sees sets proportional to their surface measure, even if that surface measure is sort of acting like r to the third as opposed to r to the squared. Okay. But here is sort of where the difference between math and truth is. We proved this with math. Fantastic. But the truth is that human lungs are fractal, right? And we do see this absorption curve. So there has to be something going on, right? Like, there needs to be some phenomenon which explains why we see these two things in nature. And so that sort of led us to try two. And the secret, of course, is that it depends on how this constant C is changing with A.
But I mean, like, intuitively understand this because you don't absorb immediately. You could go in and back scattered many times, and in this way make your way into small pockets.
Yeah, so the question was, to repeat it, somehow the fact that you reflect allows you to navigate these sort of long hallways and these twists and so on and so forth. That's exactly the intuition. And what we're going to do in the next part of the talk is quantify that exact intuition, right? So somehow reflection is an averaging property, and that's what we're trying to sort of get at here. Great. So about a year ago, Svetlana took the group of us and sequestered us in a house in Puerto Rico and didn't let us out until we understood what was going on here. And thank you to the Simons Foundation for supporting that. And by the end of the week, we had figured out what was happening. Great. So
Is there any monotonicity in this P or A? Can you say that given E, say,
yes,
how does it depend on
yes. Let's observe. By the maximum principle, I should write it all out, otherwise I sound like I'm self-promoting. By the maximum principle, UA is bigger than UB if B is bigger than A, right? So in particular, U infinity, which is total absorption, is less than UA for any other A. And of course, it's a sort of straightforward but not immediately obvious consequence that FA is bigger than FB. Oh, but now I've done this dumb. If B is bigger than A. So that was your question, right? Yeah, fantastic. And there's a similar ordering for the Robin harmonic measure as well. Okay. So let me take a portion of this boundary here and sort of re-blow up the whole thing. Right? So here's some scale R, and we want to understand what UA looks like at this scale. And we're exactly sort of trying to capture this intuition that because you can reflect, somehow you might not exit at this point, but if you reflect at this point, you probably won't exit very far from this point, right? Because you've already made your way all the way to the boundary. It seems very unlikely that you'll sort of be able to walk the tightrope and really leave this entire neighborhood before you exit. Right?
That's just about the exact definition of the reflection. I guess when a Brownian motion hits the boundary, it hits it a continuum amount of time. So what do you have a more precise idea?
I love this question. The answer is not only do I not have a more precise definition, but in fact it is an open problem in the probabilistic literature to define this partial reflection condition in the domains that are as rough as the ones that we care about. This is known as a local time variable, and it sort of is some average of how long you stay close to the boundary after you reflect. It's been constructed in certain smooth domains, but not in these sort of fractal domains, which is exactly what we cared about.
You don't employ Dirichlet in your analysis,
Only PDE, because I know zero probability, and so it's very difficult for me to employ something of measure zero. But I like talking about it probabilistically because I think it gives more intuition than the PDE. I think if Guy were giving the talk, he would talk about energy minimization, which is another way that you can think about this. Maybe I'll just point it out here, that UA is a minimizer of this energy functional subject to the conditions that it's equal to 1 on the interior, right? So this is happening in and indeed, you can think about sort of these minimization properties and think about everything in that way if you'd like. But I like thinking about this in terms of elliptic PD. Maybe also as an aside, we're actually able to address some problems in probability, some open questions about the behavior of these partially reflected Brownian motions using these PDE techniques. So in particular, this theorem here addressed a question of Bass, Birdsey, and Chen about whether or not this is true in general domains. So that was kind of fun. Yeah. Okay. So somehow the question is, if the Brownian motion hits partial omega at this point Q, how far do we expect it to get? Or if you'd like to rephrase this in terms of PDE and not in terms of Brownian motions, you can say there should exist some radius r. R will depend on A, of course, such that in a ball of radius r, we should have that the infimum in this ball of UA is comparable to the supremum of UA. Great. So theorems like this are known as boundary Harnack inequalities, and they're extremely useful in PDE. And somehow this is what's sort of capturing the physical intuition that this reflection is an averaging phenomena, right? Okay, so I think I want a different board to write the theorem. So this is joint work with the whole group of us. Currently writing it up right now. Hopefully Guy is not too angry with the draft. And it says the following. Let rho sub A be such that if you look at A times rho sub A to the 2 minus n times the measure of a boundary ball of radius rho sub A, this is equal to 1. Okay? So in particular, if your boundary balls grow like n minus 1, then you're saying that A times rho sub A is equal to 1, or that rho sub A is 1 over A. But if your boundary balls grow like a fractal, then actually there's a different relationship here. Okay? Then sup in B rho sub A of UA is equivalent to inf B rho sub A of UA is equivalent to sup in B rho sub A of U infinity. And it's this last part which is really what we're interested in here. Because basically what it's telling you, if you look at this picture, is that somehow your oxygen density is essentially constant at this scale, and the constant that it's equal to is the oxygen density up here if you had totally absorbing boundary conditions. So reflecting sort of just tells you that it doesn't matter where your oxygen is sort of randomly walking here. It's as if your oxygen was up here and would get absorbed with probability 1. Of course, what I really mean is there exists a constant C which depends on the geometry of omega such that these comparisons hold. Yes, please.
The definition of rho is also some C? Or is it depend on where you are on the boundary?
Yes, the definition of rho also depends on some C. And of course, if you make rho a little bit bigger, this is still going to be true, but then you sacrifice a little bit on the constants of comparability. Yeah. I hope it's okay that I'm sweeping some things a little under the rug here. But something weird has to be happening, because if A is so small that rho sub A starts to make you hit the interior, the windpipe, then you no longer satisfy a differential equation, right? Or you're no longer a random walk. And so there has to be some sort of phase transition. And so we also prove the following. If A times sigma of the whole boundary is less than 1, then U sub A is essentially constant.
Which is like saying it's a Neumann boundary condition.
Exactly, yes.
Constant of its one.
Yeah, so it's exactly what's happening here. What we're basically solving is a boundary layer phenomenon, which you might be more familiar with from kinetics or from fluids, right? We're saying that there's some boundary above which you don't see the boundary conditions at all. You just are walking around like a regular Brownian motion. And then at some point, a distance away from the boundary conditions start to kick in and basically tell you that you should be constant, or as constant as you can possibly be while satisfying the boundary conditions, right? So this is a phenomenon that's well known in PDE, but we actually don't know any examples of it in elliptic PDE, so we were kind of pleased by this.
Well, could I ask, I know you're an analyst, so this is
I'll just repeat the question, don't worry.
as a physicist, if you were going to write this down as from a biology model, then A would have dimensions 1 over length.
Yes, yeah, yes,
In which case, then this distance from the boundary where it starts to not, like, where it starts to just behave like Neumann is 1 over A.
yes, yes.
But you said earlier that A was P over 1 minus P, and that's dimensionless. So then I get, so maybe you've sort of something as long as I ignore the probabilistic interpretation, I'm okay.
Okay.
I just think of A as having units 1 over.
I think P actually also has units because it's really a local probability, right? It's something like absorption. Exactly, yes. Okay, Marcel is going to correct me.
There is a length scale if you use the language of P, which is the free path of your diffusion.
So
It's P over 1 minus P times the free path, and then you recover the whatever.
right. Yeah, and so this is sort of what I was alluding to at the very beginning. When we were proving this theorem, Marcel said this has to be true, and the rest of us were kind of grumpy about it. And then at some point, Guy agreed that it had to be true, and then we became less grumpy about it, and we tried to prove it. Yes, I should pull it up. Yeah. Great. Okay, I promised you an application to the total flux problem and to why lungs are shaped the way that they are, so let me give you the corollaries there, right? So. Corollary 1, there exists some constant which depends on the geometry of omega, such that if A times the total length of the boundary is bigger than this constant, then f of A is bigger than 1/2 f of infinity. So, right, our original curve was something like this. And we can't quite show that f of A is actually constant here. In fact, it's not. But we can show that you pretty much don't lose very much all the way up into this point, which you can think of as sort of 1 over the perimeter of the boundary. And then, if A sigma of partial omega is less than 1, then f of A is less than some constant times A. So we get exactly this linear growth here. In fact, we proved that they're comparable. So we're able to sort of rigorously justify this curve with these estimates up here. It's a pretty sort of immediate corollary of them. This also suggests why your lung wants to have a huge amount of surface area, right? Because it's 1 over the surface area, which is telling you the failure rate. The surface area of the human lung is roughly the size of a tennis court. So this is a pretty small number, which is great. And so we sort of have this built-in redundancy into our lungs because of this model. I feel like there was a couple. Oh, sorry, Bob, do you want to go first?
I should have asked this question before, but I'm confused about you have a fractal boundary, and yet you still keep on referring to its surface area. You mean codimension 1 surface area, or do you mean the appropriate fractal dimension?
Yeah, so to restate Bob's question, we have a fractal boundary, but the question is, what do I really mean by surface area if it really is fractal? So let me give you 2 answers, one which is less satisfying and the other one which you'll like more. So the answer is that partial omega is actually pre-fractal, right? At some point you go below the length scale, and then I can really talk about codimension 1 surface area, right? And so, but of course, what I really mean is something like hn minus 1 restricted to the boundary of omega of BR intersect the boundary of omega acts like r to the alpha for r large. Yeah.
On the first line, not the second.
Yes. Yeah. So these mean the same thing. Yeah. So this is physics and this is math. And yeah.
I think this is going to end up being a question from Marcel. What's that scale and what's that? I mean, 1 over sigma.
So R is bigger than, let's say, the cellular
So it's the
length scale.
It's the cellular length that sets that.
Yeah.
And then when you talk about that probability scaling this, the area of the lung divided by something, right? Is that the cellular area? Well, I mean, there's a unit. I mean, there's a.
Okay, I'm not sure that I got the question right. The value of the surface area is what you measure under the scale of the smoothness, which is of order several tens of microns. 10 microns. At the scale below 10 microns, the surface is smooth. So that's where you measure the 100 square meters. Right.
So then the probability of being captured is this probability that's plotting here in terms of 1 over sigma. That's measured in units of this 10 microns.
Units just complicate everything.
Actually, okay. If you want to use the language of probability, then you have to multiply by the actual mean free path of your Brownian motion. And there is an interesting game here, is that you can say that your Brownian motion has a mean free path which is twice larger. Then you exchange your probability. It's basically the p is going to change with your mean free path. So, but it's at the scale smaller than the smoothness of the boundary.
One feature of this way of thinking is that all issues about can you do the PDE you want to in this kind of rough boundary disappear because at a small enough scale.
Exactly. So you liked this answer better than I thought you would. Answer 2 is that we really can work with fractal boundaries. And then, sorry, this will get technical for 5 seconds. Then sigma really means H alpha restricted to. The boundary, and we pose everything weakly, the boundary conditions. Okay,
So we actually write in our papers HL.
yeah.
I mean, the first answer is
Yeah, but I was told that this is a mixed audience, that things should be, I'm trying to follow directions here. Yes.
Going back to the graph, you said that the x coordinate is 1 over 8?
Oh, sorry, you're right. So this should be sigma of partial omega, right? Because this is 1 over a. Yeah.
And the f, and then when, so when fa should,
No. Yeah, no, this is right, because A is going to 0, right? It's just I need to flip the, right? Yeah.
yeah, a 0 starts at the right, and goes to infinity by the time you get to the origin.
Yeah, that's right. Yeah. Yeah, and okay, I mean, something weird is happening here because, infinity is far, but yeah. Yes?
Two very close to questions. So we were talking a little bit ago about possible scaling argument that since A is the only length scale available, it's got to dominate the size of, or it's got to determine the size of the boundary layer. It seems like the cellular length scale is also available and also plays a key role. Does the cellular length scale play any role in the size of the boundary layer? And the second question, in the fractal case, is there a length scale provided at all?
Okay, so the two questions were, what's the role of the cellular layer in terms of the boundary layer? That's a great question. So actually something interesting is happening on this edge. What we're able to show is that when 1 over A is less than the cell scale, right, then actually this is also linear. So we're able to capture the behavior here and at the end, but the middle is actually very interesting and is related to the multi-scale properties of the Dirichlet harmonic measure on your domain in the sense of, say, Makarov. So we'd like to understand this better, but we don't. Maybe I should write that down so that people can see it.
No, I have to act as a chair. In the interest of time, I suggest that we move the question to the end, and we let them. Huh? No, the end is not now because there are plenty of questions.
The end is nigh, so please, only a little bit more patience.
Maybe a much less question at the end.
That's okay, yeah. People want to get to lunch anyway. So let me write something down here, which is that when 1 over A is less than the cell scale, we have f of infinity minus f of A less than C over A. Right? So this is small in this circumstance. 2, if the cell scale is much less than 1 over A, is much less than the perimeter, then we can write f of A in terms of the entropy of the Dirichlet harmonic measure of our domain. And we would like to be able to say something more concrete about how this acts, but it's hard. This is a hard thing to compute, especially when you're not in a self-similar situation in the plane. So what do I really mean by this? I mean the sum over balls of radius rho A squared, where these balls of radius rho A cover the boundary. Okay, so this is some sort of entropy functional of the harmonic measure. Okay, so I would actually be extremely interested if people had things to say about this mathematically, but also if people had intuition for why this should be true physically. But maybe we can share that after the talk. Let me end by just discussing two things which we hope to do in the future, one of which was alluded to in Svetlana's talk, and the other one was a little bit more ambitious. So, future work. So an ongoing project is to justify the shape of lungs, let's say, variationally. So what's the problem? You start with a length scale, epsilon, which you should think of as the cell scale. And what you'd like to do is find an omega which maximizes f of a for a fixed a such that the surface measure of a ball acts like r squared when r is less than omega, and the surface measure of the ball acts like r to the alpha for r much bigger than the cell scale. Right? So this would sort of, you're asking, okay, lungs should have big perimeter because that justifies this curve, but why are human lungs dimension, almost 3, while cheetah lungs have a different dimension, right? And you could ask, maybe that has something to do with the different sort of typical absorption parameters. And what we think we've found, although this is work in progress, is that we're able to show that indeed there is a value alpha for each length scale, and that when you plug in the human cellular length scale and sort of the right value of a here, you get an alpha which is pretty close to the one that humans have. So this is ongoing work with the same group of people, and maybe I don't want to say too much about it because we're still ironing out the details, but we showed that sort of maximizers exist and so on and so forth. And then the last problem is one that's quite close to my heart. So we discussed the Dirichlet problem, right? The Dirichlet problem, which is A equals infinity, but there's also the Neumann problem, which is A equals 0. And in particular, for rough boundaries, what you'd like to show is that the Neumann boundary problem is quantitatively well posed. So in particular, if you change f a little bit in an integral sense, then you change u a little bit in an integral sense. And there's been amazing work done in this direction by David and by Jill in the 90s and the 2000s. But in the types of domains that we care about, this is still a completely open problem. And maybe there's some hope that you could sort of attack this as an endpoint case of the Robin problem. But that's extremely speculative. Anyway, thank you for your patience.